One interesting feature of the Burrows-Wheeler transform is that it's invertible. So we saw that the Burrows-Wheeler transform of the string banana with the termination character is ANNB termination character AA. But given just the Burrows-Wheeler transform, I can actually reconstruct my original string. How does this work? Well, remember that the Burrows-Wheeler transform was by definition the last column of the rotations matrix that I had created. So the last column is A, N, B, $, A. The first column, well, remember I created that rotations matrix from which I constructed the Burrows-Wheeler transform by getting all rotations of my original string and then sorting them alphabetically. Therefore, the first column must by definition just be the letters of my original word in sorted order. So given just the Burrows-Wheeler transform, I can sort it in increasing alphabetical order, and that will be my first column. So remember, $sign is the smallest alphabetically because it's my termination character. So I would get $sign. Then I have 1, 2, 3 A's. So that's 1, 2, 3 A's. Then I have a B. And then I have 2 N's. Okay, so now I know that I have my last column of my matrix, and I know that I have the first column of my matrix. How do I reconstruct the actual contents of the matrix? Well, it turns out, for reasons that I won't go into in this video, that basically if I were to subscript each of the numbers, each of the characters that I see by how many I've seen of that character up to that point. So for example, $sign, this is the only one, so that's $1. This is A1, A2, A3, B1, N1, and N2. And if I did the same thing on the right side in my Burrows-Wheeler transform, sorry. This is actually A2 and A3. It turns out that this A1 is exactly this A1. This A2 is exactly this A2. So in other words, the order in which I see characters for the first time in my Burrows-Wheeler transform is the exact same order that I would see them if I just sorted it alphabetically. The proof for this I won't do in this video, but you can read the original Burrows-Wheeler transform paper if you'd like. But using this feature, how can we reconstruct the original string? So remember that basically just after, so we can think of the rightmost column being the character just before what's in the leftmost column. Right, so the $sign I know for sure was the last character of my string. Therefore, in the rotation in which $sign is in the rightmost column, this must be the first character of my string. So $sign to B1. Then B1 must have been followed by A3. Then A3 must have been followed by N2. Then N2 must have been followed by A2. Then A2 must have been followed by N1. Then N1 must have been followed by A1. Oh, actually this is A1 right here. So N1 was followed by A1, which is already here. So I've actually reconstructed my original string. Remember the $sign was at the end, so I can just move the $sign to the end. So just like that, in linear time, I was able to reconstruct my original, well, I guess technically it was n log n to sort it first. But not really. Actually, I could construct this first column in linear time as well, because I could just do a linear scan of this column, keeping track of which characters of my alphabet I've seen and how many of them I've seen, and I can reconstruct the first column in linear time. And then this searching of going around and around and around, I also did in linear time. So I can reconstruct my original sequence in big O of n, where n is the length of my string.